On August 29, 1907, 19,000 tons of steel fell into the St. Lawrence River. The entire structure dropped in roughly 15 seconds. This was the Quebec Bridge, midway through construction. It was designed to span a deep, fast-moving channel without scaffolding rising from the water, making it the largest cantilever bridge anyone had ever attempted. Late that afternoon, 86 men were out on the furthest reaches of the steel, operating pneumatic riveters and assembling the final sections of the southern arm. When the dust cleared, 75 of those workers were dead, buried in a massive pile of tangled ironwork stacked along the riverbank. Every ton of steel added to the span moved the structure toward a limit that had already been breached in the design phase. The path to the collapse begins with a single compression member and leads directly back to a desk in New York, where a mathematical error remained uncorrected for years. The 15-second collapse was the physical execution of a systemic mathematical discrepancy, finalized years before the first piece of steel arrived at the site. To understand how this happens, we have to look at how a cantilever bridge manages its weight. A cantilever is an anchored beam carrying its load outward into empty space. You balance two massive steel arms on opposite banks, and they reach out to meet in the middle. Early in the design phase, the main span of the Quebec Bridge was lengthened from 1,600 feet to 1,800 feet. Pushing the support piers closer to the shore, into shallower water, saved a massive amount of money on the underwater foundations. But extending the reach of a steel span creates a steep physical penalty. A longer bridge is an exponentially heavier bridge. Before a bridge carries a single train or pedestrian, it has to hold itself up. The permanent weight of the steel structure, the deck, and the rivets is called the dead load. When the span was extended, the detailed design calculations handled by an engineer named Peter Schlapka were never revised to account for the massive increase in that dead load. This gauge visualizes the resulting error. The physical bridge being constructed over the river was anywhere from 7 to over 15% heavier than the assumed weight written in the blueprints. Dead load is the foundational number for every other equation in structural engineering. Because that base integer was drastically underestimated, every subsequent stress model for the entire bridge was a fiction. The man reviewing those models was Theodore Cooper, an American consulting engineer with immense authority. Cooper operated out of New York, rarely visiting the site, and he refused to allow any independent engineer to check his math. Instead of catching the weight discrepancy, Cooper compounded it by altering the allowable stress. This is the maximum physical force an engineer permits each square inch of steel to bear. This chart shows how Cooper pushed the limits of the material. The conservative industry standard of the era sat at 16,000 pounds per square inch. Cooper pushed his allowable ceiling up to 21,000 and eventually 24,000 pounds per square inch. At the same time, he reduced the amount of wind load the bridge was required to resist, dropping it from 56 pounds per square foot down to 30. These adjustments served a strict economic logic. Permitting the steel to carry more force meant you could build the exact same bridge using significantly less material, heavily cutting costs. In a perfect system where the base calculations were flawless, these aggressive margins might have held. But against a dead load that was already severely underestimated, they were lethal. By shaving away the structure's safety margins to save money, Cooper systematically eliminated the bridge's capacity to absorb the uncalculated excess weight it was already carrying. All of that uncalculated pressure flowed directly into the lowest, most heavily squeezed part of the bridge, the massive lower chords of the anchor arm near the main pier. This is the specific component that failed, a compression member labeled chord A9L. It wasn't a solid bar. It was built from multiple massive steel plates, over 4 feet wide and an inch thick, stacked side by side. To keep these plates functioning as one unified column, engineers tie them together with a crisscrossing web of smaller bars. This is called latticing. Latticing forces the individual steel plates to buckle together under immense compression, rather than peeling apart and warping independently. If you squeeze a tight bundle of wooden rods, it holds firm. If you loosen the binding and squeeze again, the rods instantly splay outward in your hand. The latticing designed for chord A9L was completely inadequate for the actual, uncalculated dead load it was bearing. Under the true weight of the span, the plates inside the chord were left half loose. They began bowing outward, slowly peeling away from their inadequate bindings. At 22 minutes past 5, the latticing on A9L snapped. The heavy plates splayed outward. The instant it failed, the entire compressive load slammed across the bridge into its partner chord, A9R, causing an immediate catastrophic structural collapse. The physics of the bridge simply collected on a debt created years earlier, when the theoretical capacity of the latticing was overwhelmed by the actual deadload. A steel structure of this size rarely collapses without warning. Overloaded steel yields plastically. It bends in fractions of an inch long before it snaps. In the summer of 1907, the bridge generated clear telemetry that it was failing. Site inspector Norman McLure began measuring deflections in the lower chords. He watched them bow out of alignment, moving from 3/4 of an inch to 1 1/4 inches, and finally to 2 1/4 inches. McLure reported these alarming shifts, but off-site management dismissed them. They argued the plates were simply bent at the factory before installation, entirely missing that the structure was actively yielding under the load. Recognizing the imminent danger, McLure bypassed the standard reporting protocols. He boarded a train and traveled straight to New York to confront Cooper with the data in person. Looking at the severe deflection numbers, Cooper immediately understood the danger. On the morning of August 29th, he issued a telegram with a strict, unambiguous order: add no more load to the bridge. But the administrative machinery failed. The telegram was stalled inside the contractor's bureaucracy. It sat unread in an office while 86 men continued to drive rivets and add more weight to the span over the river. The warning signs were recorded, measured, and escalated. The tragedy occurred because the administrative pathway required to halt the project operated slower than the physical rate of the yielding steel. In the immediate aftermath, the Canadian government authorized a royal commission to conduct a rigorous post-mortem on the engineering data. Delivered in 1908, their report was unambiguous. The commission placed the blame entirely on Theodore Cooper and Peter Schlopke for severe errors in judgment regarding the undersized latticing and the unverified deadload estimates. The investigators noted that these were highly capable engineers. Their fatal mistake was intellectual hubris, choosing to blindly defend a theoretical calculation rather than verify it against the hard empirical measurements coming from the field. The remnants of that failure sat piled in the river, a devastating physical consequence of placing blind faith in a deeply flawed baseline integer. Yet the grim accounting for the Quebec crossing was not over. The decision was made to rebuild on the exact same site, using a far more conservative, heavier design. In September 1916, as the massive new central span was hoisted into position, a bearing casting failed. The entire span dropped straight into the river. 13 more men were killed, bringing the quantitative toll to 88 fatalities across 2 separate disasters before it was finally completed. This catastrophe led to the codification of mandatory independent peer reviews, ensuring that complex calculations for major structures are verified by multiple engineers before construction begins. The Quebec Bridge continues to carry traffic today, serving as a case study in the danger of prioritizing a design's theoretical economy over the physical reality of the weight it must carry.